The periodic table of elements is widely recognized, even by those who know little about chemistry. At first glance, it might seem like a random arrangement of substances with strange and foreign names. However, the table's beautiful structure reveals beautiful patterns that illustrate how nature operates.
In the mid-1800s, many chemists attempted to organize the elements into a table. Among the various formats proposed, Dmitry Mendeleev's version prevailed due to its ability to correlate existing data and predict unknown elements. He arranged the elements into rows, which we called periods, and columns, which we called groups, grouping elements with similar properties. This organization not only helped systematize known elements but also left gaps predicting the existence and properties of yet-to-be-discovered elements. Remarkably, these elements were later found with properties matching Mendeleev's predictions.
The periodic table's organization reflects the behavior of elements based on their valence electron. For example, all elements in group 1 have one valence electron, while those in group 2 have two. As you move down a group, the number of electron shells increases, but the number of valence electrons remains the same. This fundamental fact influences many characteristics of each element.
Periodic trends, patterns in the table illustrate various properties such as electronegativity, ionization energy, electron affinity, atomic radius, melting point, and metallic character. These trends arise from the periodic state nature of elements and their atomic structures, making the periodic table an essential tool for predicting an element's properties and understanding chemical reactions. Far more than just a list, the periodic table is a treasure map of the universe, with periodic trends serving as the key to unlocking its secrets.
Let's start with the basics. What is atomic radius? Atomic radius is the distance from the center of an atom's nucleus to its outermost electron. If you think of an atom like a solar system, the nucleus is the sun at the center, and the electrons are the planets orbiting around it. The atomic radius is like measuring from the center of the sun to the farthest planets. So, why is this important? The size of an atom affects how it bonds, how it reacts, and even physical properties like density. Smaller atoms pull their electrons more tightly, while larger atoms can lose or share electrons more easily. Now, let's see how atomic radius changes across a row or period in the periodic table. For example, in period 2, lithium, beryllium, and neon, as you move from left to right, the atomic radius gets smaller. Why? Because more protons are added to the nucleus, which pulls the electrons closer. Even though there are more electrons, they are squeezed into the same energy level. It's like tightening a drawstring bag. The stronger the pull, the smaller it gets. Next, let's see what's happened as you move down a column or group. I'll start with group 1, the alkaline metals like lithium, sodium, and cesium. As you go down, the atomic radius gets bigger. Why? Imagine packing for a trip. Lithium is like a neatly packed carry-on bag and small and compact. By the time you get to cesium, it's overstuffed suitcase with so many layers it barely zips. This size increase also makes cesium more reactive, like a loose zipper that pops open easily. Now, as you can see from the slides, it is group 7, the halogens like fluorine, chlorine, and iodine. Here's the trend. The atomic radius also increases as you move down. Fluorine is like a tiny balloon you blow up with one breath, while iodine is the jumbo balloon you need a pump for. It's much bigger. This size difference affects reactivity. Smaller atoms like fluorine are more reactive because their electrons are closer to the nucleus, while iodine is slower to react, like the balloon that takes more effort to pop. Finally, we have group 0, the noble gases like helium, neon, and argon. These elements are the calm and collected ones in the periodic table. Their atomic radius increases slightly as you go down the group, but their full outer shell keeps them compact. Helium is like a tiny, efficient car, while radon is like a big luxury SUV car, larger but still stable and smooth. Noble gases are stable because they don't need anything from anyone. They are the introvert of the periodic table.
Electronegativity is a fundamental concept in chemistry that helps us understand the ability of an atom to attract electrons. This property is crucial in predicting how atoms interact in chemical bonding. Electronegativity is defined as the tendency of an atom to attract a bonding pair of electrons. The most commonly used scale to measure it is the Pauling scale. For instance, fluorine, with the highest value of 4, is the most electronegative element. It means fluorine has a strong pull on shared electrons during bonding. Several factors influence electronegativity, such as, first, atomic radius. Smaller atoms have a stronger pull on electrons, hence higher than electronegativity. Second, nuclear charge. A greater number of protons increases the positive charge, attracting electrons more effectively. Third, shielding effect. Inner electrons shield the outermost electrons from the nuclear pole, decreasing electronegativity. Understanding these factors is key to grasping the periodic trends. Electronegativity increases as we move across a period from left to right. Why? This is because nuclear charge increases, which pulls the electrons closer. Secondly, atomic size decreases, which makes it easier for the nucleus to attract electrons. For example, in period 2, lithium has low electronegativity while fluorine has the highest. In contrast, electronegativity decreases down a group because, first, atomic size increases, which places valence electrons further from the nucleus. Second, shielding effect increases, which reduces the effective nuclear pull. For instance, in group 17, fluorine has the highest electronegativity while iodine has much lower values. Understanding electronegativity helps predict the behavior of elements in compounds. For example, polar bonds. Large differences in electronegativity result in unequal sharing of electrons. Second, bonding types. It determines whether a bond is ionic, polar covalent, or non-polar covalent. In short, electronegativity underpins the principles of bonding and molecular interactions. To recap, electronegativity trends are, across a period, it increases due to higher nuclear charge, while down a group, it decreases due to increased shielding and atomic radius. Mastering these trends helps us decode the reactivity and properties of elements. Electron affinity refers to how much energy is released or absorbed when an atom captures an extra electron. This occurs when the atom is in its gaseous state. For instance, when a chlorine atom gains an electron, a significant amount of energy, approximately 349 kJ per mole, is released. This is because chlorine strongly attracts the additional electron to complete its valence shell. It's essential to differentiate electron affinity from electronegativity. Electron affinity measures the actual energy change when an atom gains an electron, making it quantitative property. In contrast, electronegativity describes an atom's tendency to attract electrons within a chemical bond, a qualitative measure. For instance, fluorine has high values for both due to its strong pull in electrons, but the two concepts remain distinct. Electron affinity shows a clear trend on the periodic table. Moving from left to right across a period, electron affinity increases because atoms become smaller and their nuclear charge strengthens. This stronger pull results in more energy being released when the atom gains an electron. However, as we move down a group, the opposite happens. The atomic radius increases, meaning that any added electron is further away from the nucleus, weakening the attraction and decreasing electron affinity. While trends are useful, there are notable exceptions. Noble gases are a primary example. Their complete valence shell mean they have no tendency to gain electrons, which results in very low or even positive electron affinities. Similarly, group 2 elements have filled s orbitals that resist further electron addition. Nitrogen also stands out due to its half-filled p orbital, which is relatively stable and does not easily attract extra electrons. The ability of an atom to attract an extra electron is influenced by several factors. Larger atoms have more diffuse outer shells, which weakens their pull on and added electrons. Conversely, a higher nuclear charge enhances the pull, increasing electron affinity. Additionally, in small atoms, overcrowding in orbitals can increase repulsion between electrons, which reduces the energy released during electron addition. Electron affinity has several practical applications in chemistry. For example, it helps explain the high reactivity of nonmetals like halogens, which readily gain electrons to complete their valence shells. It's also crucial in understanding how ionic bonds form, such as in sodium chloride. Additionally, electron affinity plays a role in redox reactions by determining how easily atoms can accept electrons.
Let's talk about ionization energy. Ionization energy refers to the energy required to remove an electron from a gaseous atom or ion. The electromagnetic force that attracts electrons to the protons drops off very quickly with distance. So, the farther away an electron is from the nucleus, the easier it is to pull it away. Let's take francium for example. It is a larger atom with only one valence electron. That electron is so far away from the nucleus, making it easy to ionize. And, as we know, atom likes to have their outermost shell completely full. Losing that electron means the outer shell is gone and the atom below is now completely full. That's why an element in group 1 will easily lose one electron. Now, let's look at the opposite corner of the periodic table, helium. Helium has only one shell and its electrons are very close to the nucleus. Plus, the shell is completely full. For this reason, it requires much more energy to ionize helium. So, what can we conclude? Ionization energy increases as we move to the right across a period and from the bottom to the top of a group. And that's how ionization energy works.
I'm going to talk about metallic character, a key concept in chemistry that helps us understand the behavior of elements in the periodic table. Metallic character refers to how metal-like an element is. In simple terms, it is how easily an element can lose electrons to form positive ions, also known as cations. The more metallic an element is, the better it is at conducting electricity, heat, and forming metallic bonds. Now, let's explore how metallic character changes across the periodic table and what that means for different elements. Let's start by looking at how metallic character changes as we move across a period or row in the periodic table, from left to right. As we move across a period, metallic character decreases. Why? It is because atoms on the left side, like sodium and magnesium, lose electrons easily. They are classic metals, but as we move to right toward elements like silicon and chlorine, atoms hold on to their electrons more tightly, making them less metallic. Now, let's see what happens as we move down a group or column in the periodic table. Here's the trend. Metallic character increases as we go down a group. Why? As we move down, atoms get larger because they have more electron shells. This makes it easier for the outermost electrons to break free from the nucleus pull. In other words, the atoms become looser with their electrons, making them more metallic. For example, in group 1, lithium at the top is metallic, but francium at the bottom is supermetallic. It's like the heavyweight champion of losing electrons. Here's an easy way to remember the trend. Metals are losers, electron losers. That's it. They are great at giving away electrons. Non-metals, on the other hand, are hoarders. They hold onto their electrons tightly and hate losing them. This is why metallic character helps us understand why metals are shiny, conduct electricity, and form cations, while non-metals don't.